Hi there, Mr. Sutton here, bringing you the Algebra 2 5-2 Part 1 homework solutions on properties of rational exponents and radicals. For this problem, we have a power to a power kind of situation. In this situation, we have to multiply the exponents. So we're going to have 9 to the 2 times 1/3, or 9 to the 2/3. For this problem, we are dividing like bases, so we have to subtract the exponents. So this is going to be 6 to the 1 minus 1/4, which is going to be 4/4 minus 1/4, or 3/4. So 6 to the 3/4. On this problem, we're trying to simplify this exponential expression. So there's a couple ways we could do this. Since we have a product being raised to a power, we could actually apply this power to each factor of this product, raise each of these to the -1, and that's one way to do it. Or, since these are actually the same base in here, we could combine these together and then apply this -1 at the very end. I'm going to do that second approach. So if I'm multiplying the bases, I'm adding the exponents. This is going to give us 3 to the -2/3 plus 1/3, which is going to be 3 to the -1/3. And we're still going to have that -1 outside there. Now, if I'm raising a power to a power, I have to multiply the exponents. So this just becomes then 3 to the +1/3. For this problem, there's a couple ways to do it. One way we could do this is we could apply this exponent to the numerator and the denominator separately, raise both of these to the -1/4. Another way to do this, since we have the same exponent in here, is we could kind of undistribute this exponent from the 8 and 10, like so. So make this 8/10, all of that raised to the 4th. And the benefit of doing this is now I can just deal with these two exponents individually here. So if I'm raising a power to a power, I have to multiply these two exponents together. So we have 4 times -1/4. That's going to give me -4/4, or just simply -1 for the exponent. And I can also reduce my 8/10 to 4/5. One more thing I do need to do to get rid of this negative exponent is I need to take the reciprocal of this. So this will be 5/4 to the +1, or just 5/4. For this problem, we have a square root times another square root. So one way you could do this is individually simplify this 72 and then multiply stuff together. But I say let's multiply the stuff right away and see what we get. See if it's maybe a perfect second power, perfect square. So 2 times 72 is 144. And 144 is a perfect square. The square root of that is just 12. So we're actually done. On this problem, I notice I have a 5th root divided by a 5th root. So one option I could have here, if I don't want to try to simplify this numerator and then move things together, is I could immediately divide the 486 by the 2 and put it under one big 5th root. So 486 divided by 2 is 243. So this is just the 5th root of 243, and that's just 3. For this problem, we're trying to simplify the 4th root of 567. So one thing I want to check right away is to see if 567 is a perfect 4th power. Let me just take the nth root of 567. So this will be 4 and then 567. And that comes out to a decimal. So no, it's not going to be enough to just take the 4th root of that. So one thing I do want to check then is if I can split this into a perfect 4th power times something else. So perfect 4th powers, we've got 2 to the 4th, which is 16. Definitely 16 is not going to go into this because it's even versus an odd there. Let's see, 81 is the next perfect 4th power. That's 3 to the 4th. 567 divided by 81 is exactly 7. So that split actually works out. So I will break this up into the 4th root of 81 times the 4th root of 7. And 4th root of 81, again, that's going to be 3. So this is just 3 4th root of 7. For this problem, the reason this is not considered simplified is I have a radical in the denominator. One thing I could try is maybe merging the 5 and the 4 together and taking the cube root, but that's actually not going to do anything useful. So I'm going to have to instead rationalize this denominator by multiplying the top and bottom by something that will make this a perfect cube down here. So let me think. 4. What perfect cubes does 4 go into? Well, the first perfect cube that I can think of is 8, and 4 definitely goes into 8 2 times. So if I multiply this by the cube root of 2 over the cube root of 2, that'll give me the cube root of 8 in the denominator, which I can then take the cube root of and not have a cube root anymore. Now in the numerator, I'm going to get the cube root of 10, which is just whatever it is. Doesn't really matter. But the cube root of 8, that's going to be 2. So we've got cube root of 10 over 2. For this problem, this is considered not fully simplified because I have a fraction inside a radical. So if I can't cube root this right away or reduce it and cube root it or anything like that, my only recourse is to split this up into two radicals. So I can write this as the cube root of 64 over the cube root of 49. Now the cube root of 49, I can't really do anything with that, but I'm going to try to turn this into a perfect cube by multiplying it by something. So what's a perfect cube that 49 goes into? Well, 49 is already 7 to the second power, so it definitely should go into then it should go into 7 to the third power. So if I just multiply this by a cube root of 7, that will give me a perfect cube down here. It'll give me 7 cubed, whatever that is. What is 7 cubed? I mean, just out of curiosity, 7 to the third power is 343. Okay. So when I multiply this out, I'm going to have the cube root of 343 in the denominator. And upstairs, I'm not going to bother doing 7 times 64 because 64 is already a perfect cube. The cube root of 64 is just 4. So I'm going to write my numerator as 4 cube root of 7 and the denominator then as cube root of 343. But then I can immediately turn around and take this cube root to get 7 in the denominator, and now this is fully simplified. For this problem, which is the first of two problems that are in the honors version of this homework, we have two terms in the denominator, one of which is a radical. So that tells us we need to multiply by the conjugate of the denominator. So I'm going to multiply by 1 minus radical 3 over itself. And that just gives me 1 times 1 minus radical 3, so 1 minus radical 3 in the numerator. Now the reason I did this is because in the denominator I can use my a squared minus b squared factoring foiling sort of shortcut. So 1 squared is 1, the square root of 3 squared is 3, and then I have a minus between those. So then just doing a little simplifying down there, I can make this 1 minus radical 3 over negative 2. For this problem, we have not one, but two radicals being added together in the denominator. Because I've got two terms here, I'm going to try multiplying by the conjugate to untangle this thing. So that means I have to multiply by radical 3 minus radical 7 over itself. In the numerator, all I can really do is just distribute this 9 to both of these. So 9 radical 3 minus 9 radical 7, nothing else to really do up there. In the denominator, I can use my a squared minus b squared shortcut. So the, let's see, radical 3 squared is 3. Radical 7 squared is 7, and I'm subtracting that. So this just simplifies to 9 radical 3 minus 9 radical 7 over negative 4.